Hello dear student, welcome on this video lecture. We are discussing about vectors and vector algebra. In vector algebra we have talked about lot of basic things. Now we will be moving ahead. So before we go ahead, there are some points we need to recap them, and then we need to connect what we are going to study in this video. So if we have been given vector A and vector B, two vectors, so we can have lot of operations between these two vectors that we have talked about. Operations like we can go for the addition, we can go for the subtraction, we can go for the multiplication. In case of multiplication, you have understood two different types of multiplication. One was a cross product and another was a dot product. So these operations, they occur between two vectors. We do not have divisions of vector. As we stated initially, the division of direction by a direction is not permissible. But multiplication we defined, multiplication of directions we defined in two different ways. One dot, another is a cross. So this was related to operation or algebra when two vectors are involved, A and B. Now what happens when more than two vectors are involved? So how we do these algebraic operations? Addition we know how to do, we can add them up. Subtraction we know how to do, we can subtract them. But main important point is how we operate these multiplication or product. So let's try to understand what can be the possibilities. Let's say we have a vector A. Let me write it smaller. Vector A and vector B and vector C. So these three vectors we want to multiply. Now what are the options available? There are going to two places where the operations has to be assigned. One may be at this location, another at this location. Now what the options of filling these two spaces is a cross and a dot. So as we think about, we can say there can be dot, there can be cross, dot, there can be dot, cross, and the next option could be cross, cross. These are the four possibilities that can be filled between these two spaces. Moreover, whenever we do these products of more than two numbers or quantities, we do two at a time. So if we are doing two at a time, so let's say start this B and C we are performing, and then if we are performing this B and C, so we will be having these two options. That means we will performing this dot first, then we will be getting this, then doing this dot. Another option can be A and putting a cross over here and doing this dot. Another option could be like putting a dot over here, doing cross over there. And the final option could be like A, doing cross over here and cross over here. Now if you look carefully, and let's try to understand, are all the operations, these four operations that I have assigned or represented here, are they possible? So first let's talk about this first one. So this first one is trying to say, first we are going to go for the dot product between B and C. So we will apply the rules of dot product, and we know dot product rules as B, C, cos theta, where theta is going to be angle between B and C. Moreover, this is going to be scalar quantity. Since after solving this, we are going to get this as a scalar quantity. So this becomes a scalar and this is a vector. Now we know we place this dot between two vectors and not between vector and scalar. That means here in the first operation, we will finding something like a vector having dot product with a scalar quantity, which is not defined. So we will say this kind of operation is not defined. Making sense? Now let's talk about the second type of operation. In this second type of operation, again the same problem you will face, that this B dot C has to be performed first because this is placed inside the bracket. So we first solve the bracket, then go ahead. So this becomes again a scalar quantity, and this is scalar quantity with this vector quantity. We are supposed to find a cross product. So we know that this cross and this dot, they are performed between two vectors. So it has to be vector, but it is not a vector, hence this will also not be defined. So we will say this is not defined. So you won't be asked like this first or neither like this too. If they are asked, then you say answer is not defined. Let's talk about the third. Can we say whether this third can be having a some realistic meaning, or is it defined? So you will say yes. B and C first they are going for cross product. After doing this cross product, this will become a new vector. Since this is a new vector, and this new vector can be made a dot with another vector A, and we know the dot can be operated between two vectors. So first we will be simplifying the cross, then we will be simplifying the dot, and finally we'll get some answer. So this is defined. So this is defined. Now what the final answer is going to be, that we can also think of. Final answer is going to be a dot product of two vectors. That means final answer is going to be scalar number. So this third will be defined and it's going to be scalar ultimately. So we will call it as a scalar triple product. That means we will call it a triple product because we are using three vectors or three quantities and doing product. So that's a triple product, and this triple product yields scalar quantity, hence it will be known as scalar triple product that we are going to start with. And there's going to be fourth way of operating these cross and dot between these three vectors, which is here. So first we are going to do this bracket settlement, which is a cross product, so which is going to give us a vector quantity. This vector will be multiplying another with another vector in a cross fashion. So again we can define this cross fashion between two vectors. Moreover, this is going to give us a vector quantity. So we will say yes, it is defined and it is going to be a vector. So result will be a vector, hence this type of multiplication of three vectors will be known as vector triple product. So whenever the three vectors are given to us, we need to do product, then we need to think about which one is defined, which one is not defined, then we need to think about which will give scalar value, which will give vector value. So first two in this example are not defined, the rest of the two they are defined. Third is indicating a scalar result, hence scalar triple product. Fourth is indicating vector result, hence it will be known as vector triple product. So let's talk about this scalar triple product, which we can in short say STP, scalar triple product. Now for this scalar triple product, we need to have a three vectors, A vector, B vector and C vector, and we need to do cross between two vectors first. Whatever the result will come, this result has to be done dot with another vector, and answer will be coming as scalar number. So this is called scalar triple product, as we just talked. Now this is also indicated by this symbol. That means we make a big bracket and we write A comma B comma C. So if this kind of symbol is given to us, we will say that this is representing scalar triple product between two vectors A, B and C, between three vectors A, B and C. Now that means this is going to be equivalent to this, that means A dot B cross C. Now this can also be written in a different manner. That means we can say this is also going to be equal to, now we can think of some properties of it. So this can also be written as this B vector dot C vector dot A vector. That means if we change this order from ABC to BCA, it remains the same value. And if we want to write in terms of this, so we can say it's written basically B dot C cross A, C cross A. Moreover, this is also going to be equal to, in the same cyclic order, C, A and B. So this value, which is also going to be equal to C dot A cross B. So if the three vectors are given to us and we are asked to find the scalar triple product, either we find A dot B cross C or B dot C cross A or C dot A cross B, we will find all the values are going to give us the same result, or all the operations will give us the same result. So that's called scalar triple product, and they are also indicated by this big bracket and writing them in order. Now if you try to observe what is going on, it's like A B C, then B C A, then C A B. That means there is a particular way of order that has been observed. However, if we change this order, then there is a difference. So let's say that we can think of, because we know already this cross product and dot product. If suppose somebody says we need to find B, or let's say we need to find this A vector dot C cross B. If we need to find this, then we can use that this is also equal to A dot, and this C cross B can be written as minus B cross C, because we know in cross product if we exchange the position, then minus sign comes in, and this minus sign undergoes this dot product, so we know this will come outside, so it will become minus A dot B cross C. Now if you have understood what I have done over here, so I have just said that if we are exchanging the locations of cross product elements or vectors, then there is going to be a minus sign coming in. This can be rewritten as this scalar triple product of A, C, B is basically equal to minus of scalar triple product of A, B and C, right? Moreover, this A, C, B, this order of scalar triple product will be equal to maintaining its order. That means we can say this is also going to be equal to this, or let me write this as well, A, C, B. This will have the same value as C, B, A, which will have a same value as B, A, C. So there are two types of orders going on you need to take care of. So let me quickly re-explain what we are focusing over here is this particular arrangement, that means having one dot and cross, is called scalar triple product because they are using three vectors and it is giving you a scalar quantity. That point is easier to grasp. Moreover, whenever these three vectors are to be multiplied, we will place this bracket with the cross product, because first we need to do cross product. If we are doing first dot product, then that will become a scalar quantity, that won't work for future calculations, right? So this bracket has to be placed with the cross product up to vectors, and that will be a vector. This vector has to be multiplied in a dot fashion with another vector, so it's going to be a scalar number. Then a property I have explained over here, that if you do A dot B cross C or B dot C cross A or C dot A cross B, they are going to give us the same value. How we can check that? We can take any vector A, any vector B, any vector C and do this first, then this, then this. You'll find all are going to give us the same answer. So here I have just explained the result. Moreover, these notations can also be written in this way. We will have a bracket, big bracket, and we will writing them in order. So if it is written as A, B, C, that means it is A dot bracket B cross C. Similarly, this can be written in this format. That means B vector has to written first, then C, then A. Similarly, C, A, B over here. Right? So this can be verified by taking any value of A, B, C vectors. Moreover, if we take this order different, that means if we take A dot C cross B, then it came out to be this brings a minus sign with the initial or earlier this value. So it's like this. If we have vector A, then B, then C, then we can find the cyclic order like A, B, C, then B, C, A, then C, A, B. They all will give us the same value. But if the order is reversed, that means any two orders are reversed, then you will find this value will be negative version of this value. So changing the position of any two vector will result in a minus sign. So swapping or exchanging two positions will bring a minus sign. If we keep on maintaining that order, then the value remains same. Now this can be verified by taking any values of vector A, B, C and D. If in the examination, suppose in written examination board or somewhere you find that prove this, that this is the case, then what we need to do, we will consider A as a vector A1 I cap, A2 j cap, A3 k cap. Similarly, we will be considering the vector B, vector C, right? And then we will take this and then we first perform cross product between B and C, then whatever it counts we will perform dot product with A, then see what the number is coming, then we will repeat this expression, then we will repeat this expression, we will find all the values are going to be equal, then after we can operate this expression, then we will find this result will be negative of all the previous values, hence they will be verified. Making sense? So this is called scalar triple product, and that's how it is represented, and this property says that in order they have the same value. If the two positions are swapped, then it becomes a minus number. There are some more properties that we are going to learn, so let's move towards the next slide. Now let's consider this expression, which is written as A vector and B vector. That means what we are doing is we are trying to find out the scalar triple product of these three vectors in which two vectors are identical. So we need to find this value, which is going to be basically equal to A vector dot A cross B. If someone asks what this value is going to be, then you can think of what this value is going to be by using the concept that we have already gone through. So just think what this value can be, in which we are trying to perform this scalar triple product of three vectors such that the two vectors are same. So it's going A vector dot A vector cross B vector. By now you might have thought what the answer is going to be. Now look at this. This vector is a cross product between vector A and B. Then that means this vector is certainly going to be perpendicular to vector A and perpendicular to vector B. So this must be perpendicular to vector A as per the definition of the cross product. So since this is perpendicular to A, then whatever this vector is, this vector has to be multiplied in a dot fashion with vector A. So ultimately you are doing a dot product of vector A and another vector which is perpendicular to this vector A. That means this dot product is occurring or taking place between two vectors which are perpendicular to each other. And we know when the two vectors are perpendicular to each other, then answer comes out to be 0 in case of dot product. So dot product of two perpendicular vectors is 0. So from here we can think of one point, that if the two vectors are identical and we are doing this scalar triple product, then the answer is always going to be 0. Moreover, this can also be said by using this thing, because we know if we change the order, its value remains the same. That means this could also be written as, let's take this A in this side and shift entire it. So it's going to be equal to some sort of this vector A, comma vector B, comma vector A again. And if we make this one more cyclic order, so it's going to be some sort of this B vector, comma A vector and A vector. Now if we expand and write in terms of dot and cross, it's going to be B dot A vector cross A vector. Now slowly and surely you will be using those cross product and dot product rule that you have already learned. One of the rules we need to use over here is a B dot A cross A. So first we are going to settle down this cross product. Now one rule that we have understood is that the cross product of a vector by its own is always a null vector, because they are the parallel or collinear vector, and cross product of collinear vector is 0 or null vector. Hence you'll find this will become null vector, and null vector is multiplying with any vector will give us 0 as a result. So that's going to be null vector. Hence our answer finally will become equal to 0. Now final answer has to be given as a 0, not 0 vector. The reason you know, because final answer is a numerical, because this is scalar, it's not a vector. So this red color is a 0 vector, whereas this black 0 is a 0 number, and there's a difference, you know that. So that means from here we got a rule: whenever the two vectors are identical, then you will find that the answer is 0. Moreover, you can go more a bit deeper as well. If the two vectors are not identical, still you will find the answer can be 0. Use this. If the two vectors are collinear, then you'll find answer will be 0. So even if we write as A, B, C and claim A and C are collinear, then the answer will become 0. So for collinear vectors, you'll find this becomes 0. Making sense? Great. Let's talk about one more property. Let's say we have three vectors A, B and C. So I'm writing as this hashtag over here. Let's say three vectors are A vector. So let vector A, vector B and vector C all lie in the same plane. So they are in a plane. Whenever the vectors lie in a plane, we call coplanar. They are, let's say, coplanar. Then we need to find, then we want to know what this value is going to be, A, comma B, comma C. When we write in this manner, that means we are talking about basically scalar triple product. So the given thing is that A, B, C are coplanar. That means all the three vectors are lying in the same plane. So if I draw, I can draw all of them in this plane of board. So let's say this is A, this is B, and might be there somewhere is a C. That means all the three have been shown in the plane of board or this whiteboard that you are able to see. So that's called, these three vectors are coplanar. Now if they are coplanar, what the value of this A cross this A, B, C scalar triple product is going to be? That's also an important result we need to remember. So before we write the final result, let's try to understand how this result is achieved. So we will be expanding it like this: A dot B cross C. As per calculations, this will be operated first. When we operate this is going to be a vector, as we have talked about. This is a cross product. That means this is going to be in the direction of n cap. And you know this n cap is going to be perpendicular to B, perpendicular to C. That means this n cap is going to be definitely perpendicular to the plane in which B and C lie. So this n cap is going to be perpendicular to the plane of B and C. In this picture, if you see, this is the plane of B and C. That means this white plane that you can see, this is the plane of B and C. Making sense or not? Hence this n cap is going to be perpendicular to this plane, either outward or inward. In this given particular situation, B cross C, using right hand rule, if you do your right hand, if you place your right hand fingers in the direction of B and curl towards C naturally, then thumb will be outside. So that means you'll find this n cap is going to be outward, but that's not required. What is required, that n cap is perpendicular to the plane B and C, and then you can connect. Now this is perpendicular to B and C. That means it is perpendicular to the plane in which B and C lie. And since A is also lying in the plane plane of B and C, that means this vector n cap is perpendicular to the direction of this vector A. Hence again this dot product is taking place between the two vectors which are perpendicular to each other. And whenever the two vectors are perpendicular to each other, dot product is always 0. Making sense? If you have understood, it's good. Otherwise you can rewatch what I have said. So based on this, we got one result, an important result. This result says whenever there are three vectors A, B, C and they are coplanar, then this scalar triple product must be 0. Making sense? This must be 0. So that we will be using as a condition for coplanarity. So coplanar vectors will have their scalar triple product 0, and that can be guaranteed. Okay. As a next point, let's talk about how to find the value of scalar triple product if the vectors A, B, C are given in this I cap, J cap, K cap form in 3 dimension. So let's say we need to find this A vector, comma B vector, comma C vector. That is basically scalar triple product. So we know, for that sake, what we need to do, we need to go for the cross product first between the two vectors B and C. So first we will be doing the cross product between vector B and C, and then whatever the vector turns up finally, that has to be operated as a dot with vector A, and whatever this is going to be, that will become our answer. This can also be found out by using the determinant method. That means this is going to be equal to this determinant. So if we know the opening of the determinant, which we have talked about in the previous video, in case of cross product, so that determinant will be that can be used in here as well to find this value directly. So we will be making this kind of determinant, and here we will be writing the coefficients, corresponding coefficients of three vectors. So in the first row we are going to write the coefficients of first vector, that is a. So we are writing it as a a1, a2, a3. In the second row we will be writing the components or coefficients, corresponding coefficients of second vector. So that's going to be written as b1, b2, b3. And finally at the third row we will be writing about this third vector, which is c1, c2 and c3. c1, c2 and c3. Making sense? Since this is going to be a scalar number, that's why we are not writing I cap, j cap, k cap, because once we write I cap, j cap, k cap, that our answer becomes vector. So three vectors will be occupying their positions, like first vector's coefficient, second vector's coefficient, third vector's coefficient. And we will be opening this or expanding this the way we have understood. That means about the first row, so we're writing this first element a1 as such. Then we will be not using the first row, first column, then we are multiplying this diagonally. So it's going to be b2 c3 minus b3 c2. So that will become the first term, and then we will write this a2 but with a minus sign, and we'll be expanding it about this. So the row and the column, it will not be counted, so it will be b1 c3. So it's a b1 c3 minus b3 c1, and finally we'll be writing for a3. So it's going to be a3, and corresponding row and column will not be considered, so it will come out as a b1 c2 minus b2 c1. You can check from this. So if we want to do this a, b, c, or that means scalar triple product of three vectors quickly or directly, we will be using this determinant and expanding, will be getting our answer. This final answer is going to be numerical value. Now this is going to be more convenient, because otherwise first you need to do this cross product, then you need to dot product, ultimately you will get the same answer back. So we can use it, right? So from here we can think of one rule that we that relates to the previous property. If somebody says a and b and c are coplanar, so we will say a or let me write in short. If somebody says if a, b and c are coplanar, so what is the condition? So we will be using that condition that we have learned. Then we can claim this determinant is 0. This determinant is 0, or in short we can say a, b, c, scalar triple product of these must be 0. So sometime it will be asking you that the three vectors are coplanar, find the unknown quantity. So we will be using this determinant, will be simplifying it and putting it to 0. Once you put it to 0, then you will get one equation and one unknown can be solved. So that will become a type of question for examination. Another important application of this scalar triple product is about the volume of parallelepiped. So let's talk about this figure. See this figure. This figure is made up of three vectors. So this is indicating vector A, this is indicating vector B, which is going inside. That's a three-dimensional figure, and this is a vector C. Right? So this entire figure can be constructed by using these three vectors, because you can see this vector, if you draw this vector is basically parallel to A. So this is vector A, this is also a vector A, and this is also a vector A. So we have used this kind of four vectors A. Similarly, this is going to be B, this vector is going to be B, this vector is going to be B, so four B vectors, and similarly these four C vectors are going to be involved. So that means if we know three vectors which are non-coplanar, then they will be creating a geometry called parallelepiped, and this three-dimensional geometry will have its volume. Now the application of a scalar triple product is to calculate this volume as well. So we can calculate this volume, that means volume of this parallelepiped. So if sometimes question is asking find the volume of a parallelepiped formed by three vectors A, B and C, and A, B, C will be given in the form that means A1 I cap plus A2 J cap plus A3 K cap and so on, then we can write this, and this volume comes out to be V is equal to the value of this determinant, or you can say this scalar triple product. So whatever the value of this scalar triple product is going to be, that becomes the volume of this parallelepiped. The one thing that we need to thought about, that this is going to be a scalar number which can come as a positive as well as a negative, but this volume is always going to be positive. So for that sake we place a mod sign with this. So we will say this value of the volume of parallelepiped is going to be the mod value of this determinant or scalar triple product. So this you can treat as a formula, and in future whenever it is being asked, you just use this formula and find the volume of parallelepiped. So these are the applications and properties related to STP, scalar triple product. You need to make your notes proper and jot them down. If the question comes in, A, B, C vectors will be known to you. You just find this determinant. Popularly, two types of questions you can watch. One, to find this A, B, C as coplanar vector. So place that determinant as 0. Another, volume of parallelepiped. So calculate the volume of parallelepiped. Just calculate this determinant value and say the positive answer. Okay, now let's move ahead. Well, there is one more application of this scalar triple product. So let's consider this first. It's a volume of a tetrahedron. So what is a tetrahedron? Let me explain that. So let's say we have three vectors, A vector, B vector and C vector. As we saw just before that using these three vectors we can create a parallelepiped, right? Similarly, using three vectors we can create another three-dimensional geometry having volume. So if we have three vectors, let's say see this figure, which is a big figure. One vector is this A vector, and another vector is B vector, another vector is C vector. All these three vectors are not coplanar, that means they are in this is a three-dimensional picture, but all the three are co-initial, so they are starting at this point. So once we draw all the three vectors, then you will find the heads of three vectors will be free. Now these heads points, if we join, so we will find that there's going to be a three-dimensional geometry creation. Can you see that? So this is the head of A, which is being joined with the head of C, which is further being joined head of B, and then this head of B is further joined with head of A. So you will have this kind of geometry, which you can visualize as that there are going to be couple of triangles there are triangles, triangular surfaces. So you can see this is a triangle at the base, and this is the triangle on the side, this is triangle on this side, and there is another triangle on another side. So you can say this tetrahedron is made up of four triangles or four triangular surfaces. So if somebody asks what the volume of this is, so volume of this tetrahedron is also calculated using this scalar triple product. So formula for this comes out to be 1/6 of the scalar triple product value. So scalar triple product value, which is A, B, C, mod of this value, 1/6 of that number is the volume of this tetrahedron. So the two geometry that we have talked about, they are very similar to the case that we dealt in the cross product. In cross product, by using two vectors, we were able to draw a triangle as well as a parallelogram. Whereas by using three vectors, we are able to draw two geometries. One is tetrahedron, another is parallelepiped. And for these two, both of the geometries, we are able to write the formula. Formula is 1/6 of STP of ABC for tetrahedron and STP of ABC as a modulus value for parallelepiped. So if A, B and C are given to us, we can also find the volume of tetrahedron. Now the proof of this can be considered if you go for the mathematics. In mathematics you will be talked about various geometry and how to get the volume. If I give you a hint, then that will be sufficient. The hint that the volume is going to be the base area into perpendicular, or the height into divided by 3. So volume is 1/3 base area into height. Once we can find height and simplify, it will come exactly equal to this. So that proof is not relevant for us, but yes, this formula is relevant for us. If they are going to ask a question, they will give you A, B and C. They will ask simply find the volume of tetrahedron. You simply find this and that will be our answer. Making sense?